where tomorrow your final slides are due. Make sure that you include that slide at the end that talks about what revisions you made based on the peer reviews or whatever you decided to base your revisions on. The expert TA, all of it is due on the 9th as well. Downloading those on Saturday, so there's no going back after that. Although you have all of tomorrow to do any expert TA you want. There is a quiz over the weekend over chapter 16, due Sunday night as usual. Tuesday, we're doing the presentations, and you can either come to class at some time, 2:45, perfect, thank you, at 2:45 and present, and then you'll be done with the presentation. Or you can record your presentation, put it on the forum in week 16, also on Tuesday, and for that one you'll have to reply to other people's posts as well. Then you have the final assignment, which is the reflection on this project, where you will tell me what you liked, what you didn't like, and what you would change in, I think, 300 words. Due Friday the 16th. Is that all good? Okay. Look here. I am hoping to have the grades done by Monday the 19th. So if you all could go to iLearn and check your grades on the 19th, make sure I didn't make any horrific errors, I'd appreciate. I'm going to submit the grades to school on Wednesday the 21st. So, and I'm probably going to do that in the morning. So if you really need to have your grades checked by Tuesday, because after that, if I made a mistake, it gets much more difficult to fix. Sound okay? Yeah, so all the quizzes graded, the slides graded, everything finalized. So what you see on Monday is what I have.
On Monday the
19th. And then, yeah, you have until the 21st where I'm just going to put it all into the faculty website. And after that, you have to wait until next semester to get it fixed. Okay. That's everything. Everyone pretty happy? Okay. A couple of my other classes have been worried about like technology. If you come to class and present, I have a USB-C connector. So if you want to bring a device with a USB-C, that's great. I also promised my other classes that I turn on the Zoom. So if you wanted to present via Zoom, that's fine. And that's also makes it pretty easy because you can just share your screen. And
USB-C.
I have USB-C, yeah. And yeah, you could just do that. I think you did that last semester anyway.
Yeah, because the projector was being very difficult to deal with.
Yeah, so yeah, it's really fine.
Have you just sent the presentation to you and use that?
Yeah. Okay. So, but I'm on a cheap Chromebook, so I can't open PowerPoints. Don't trust me to be able to play videos.
Okay.
Yeah, but yeah, if you put it somewhere, I can open anything Google.
Okay.
What do we got? Choice. Yeah, so you can just record your presentation and put it on the forum, and you'll be done there. Although there you have to make replies to other people to mirror the community that we have here in class. Yes, although I'll probably give you an extra 24 hours on that. But yeah, definitely try to get them due. The replies, you can have them due on Wednesday. Just your videos have to be up on Tuesday. Okay. Yeah, video, I'm assuming that's video recording. Okay. All right, so we're all, man, these, so I did this looks good. Okay, so we are pretty far through this chapter. We don't have that much more to go. So I'm going to, unless there are any other questions, sorry. Questions? Okay, we're pretty far through this chapter. So I'm going to finish it up. We'll have plenty of time if anybody has any questions on the homework or previous homeworks or anything like that. So if you want to take a minute to look through the homework, that's a smart idea. If not, we might end a few minutes early, but like we have lab anyway, so. Okay, so let's do this then. Sorry. I need to share this screen. Whew. Okay, here we go. So we had left off. We were we had done some kind of messy math that had given us a wave equation that said, it didn't say that, it said, this. It said the partial derivative of either the electric or the magnetic field, but I'll put electric here. The partial derivative of the electric field with respect to space, second partial derivative of the electric field with respect to space, equal mu naught times epsilon naught over the second derivative of the electric field with respect to time. Okay. And then we had said, well, why don't we use, since we know that we have this equation that says if you take the second derivative of the equation, you need to end up back where you started. Why don't we use a sinusoid, a sine or a cosine? Because those, if you take two derivatives of a cosine, you get a cosine back. So we use cosine. And we see that it needed to be a function of space, which is x, and time, which is t. And so we added in a space and a time variable to that, where we multiplied them by constants, because that'll tell us how scrunched up or spread out our wave is. And we also put a amplitude, an Emax, in front of that. And just so you know, you can go through this, do the exact same thing, but put magnetic fields B in place of every electric field E. You get the same answer, because they're two sides of the same coin. And so what we did was we took two derivatives with respect to x. We took two derivatives with respect to t. We multiplied the derivatives with respect to 2 by that mu naught epsilon naught, and we set them equal to each other to see if they were equal. And we found that as long as our constants satisfied this, yeah. No, we're not. My projector game is great. Okay, as long as this is true, then our solution works. And then we started talking about what these constants are, where omega is the angular frequency, 2 pi f, and k was kind of the same thing, but for wavelengths. It was 2 pi over the wavelength. And so at that point, I wanted to talk about an equation, v equals f lambda, which is true for all waves. But I wanted to talk about why this is true. So like, if I have a wave, basically it's something that's going up and down like this, where this value is the wavelength that we call lambda. You would measure that in meters because it's a length. Sound okay? Okay. This thing is also moving. So this is like water waves that you see in the ocean. So these waves are coming at you. And the time it takes this particular spot on the wave to move one complete wavelength is called the period of the wave. So if you're looking at water waves coming at you and you said, okay, the first peak passed, the time it takes for the second peak to get there, that would be the period. And you would measure that in seconds because it is a time. And so if I wanted to look at the velocity of this wave, I would say, well, velocity is distance over time. So if the wave has traveled one wavelength, that by definition has taken one period worth of time. And since a period is 1 over the frequency, or the frequency is 1 over the period, this equals lambda f. Does that make sense? Okay, so notice we did this for water waves. It's true for all waves because all waves you define by a wavelength and a period. So no matter what time of wavelength you have, this is just a basic definition sort of equation. And so let's go back to this guy right here, where after some scooching around, we put 1 over mu naught epsilon naught equal to omega squared over this wave number squared. This is called a wave number. Wave number. Number of waves you can fit in 2 pi, basically. Okay, and that's a squared. Where if omega is 2 pi f and k is 2 pi over lambda, our 2 pi's cancel out, and we get an f squared lambda squared equals 1 over mu naught epsilon naught. And so now hopefully you're looking at that f lambda and you're saying, hey, that's really a speed. So this is a speed squared. So this is a speed squared equals 1 over mu naught epsilon naught. And if you square root both sides, what that gets is that the velocity of light, literally light speed, is equal to 1 over the square root of mu naught epsilon naught. And if you think about what mu naught and epsilon naught mean, hopefully this makes kind of sense, because epsilon naught was how easy it was for an electric field to get into a vacuum, like a space. Mu naught was the same idea, but for a magnetic field. So we're saying that the velocity of light is proportional to how easy it is for electric and magnetic fields to get into that area. Make sense? Where you can also calculate like the speed of light in air by putting in the constants for air, the mu for air, the epsilon for air, or water, or diamond, or whatever you want, really. You'll find for air and for vacuum, it's identical-ish. But even more, you can take those constants, because we have gone over what they are, and you can throw them into your calculator. That's the meters per amp. That's mu naught and epsilon naught 8.85 times 10 to the negative 12th. Coulomb squared, Newton meter squared. Okay. And if you do that, you'll wind up with 3 times 10 to the 8th meters per second. And do you guys recognize that number? Yeah, that's the speed of light in a vacuum. So, speed of light in vacuum. Okay, so that's where this number is coming from. Now note, of course, you're going to get a different answer if you're in a diamond or in water or in some other material. But in a vacuum, that's how fast light moves. Okay, things I need to say about this. This is true for all light waves. So in lab today, we're going to calculate the speed of light using a microwave, where a microwave has wavelengths of like a cut centimeters. Its wavelength is in centimeters. But the entire spectrum is going to follow this: radio waves, colors, microwaves, gamma rays. They're all part of a spectrum. And so kind of one important thing about light waves is to remember that everything on the spectrum behaves the same way. So very high energy gamma rays behave the same way as very low energy radio waves. They have a frequency, they have a spectrum, they have electric and magnetic fields. They can propagate themselves through a medium or even a vacuum. Sound okay? Okay, I really like that. Everyone solid on that? I hope so. So I don't want to do this demonstration because this demonstration is pretty cool. Let's look at antennas really quick. So I drew an antenna for you last time, right? I drew like the metal rod with that. I have an antenna right here. This is a microwave transmitter, not like the first one. But you notice it's got an antenna. So that's what this is. It's just metal things where they're going to oscillate electrons up and down. And so when you see an antenna, yeah, you really just to put a signal across here where your plus charges and your minus charges oscillate. So they wiggle back and forth. And when they do that, they will make magnetic fields like that. Because wiggling is a really good way to accelerate things. And remember, we had this idea that if your charge was stationary, you just had an electric field. If your charge moved with a constant velocity, you got a magnetic field that was constant. But if your charge accelerated, that's when you started getting electromagnetic waves, because you had that magnetic field that changed and that created the electric field and so on. And the same thing is going to happen here. Your magnetic field is getting larger and smaller as your charge wiggles back and forth. That's going to make an electric field that looks kind of like this, because you have positive charges on one end and negative charges on the other, like so. And then what's going to come off is these magnetic fields and these electric fields are coming off like this, where your electric fields are going to go up and down like that, and your magnetic fields are going to go side to side. So that when you have your receiver, you want to position your receiver so that the electric fields cause it to oscillate. And really quick, let me show you this demonstration. Okay. No problem. I'm smart enough. Okay, here we go. So I'm going to turn this guy on. It's going to take a second to warm up. But so it's oscillating, and we have this thing, which is a receiver. So it's got, I don't know if you can see, but it's got a little antenna inside it too, that you notice is lined up here. So the electric fields here are going to line up with the electric fields here. Okay. Okay, and so I'm hoping you see that we have a fair amount of energy coming through here. But now, what I'm going to do is I'm going to put this metal grating in front of it. And all of a sudden, we have less energy. I'm going to hold on a second, because I'm going to do this. The metal grating is still in front of it, but is no longer blocking the electric field. And so let's talk a little bit about how electric fields act inside conductors. Do electric fields exist in conductors? No, right? Conductors shield electric fields. So when we put there we go. When we put this in this direction, it is not shielding electric fields. Does that make sense? Electric fields are passing through it. And that is because these electric fields that are going up and down, it will cancel out the electric field right here, but if our electric field extends this way, it won't. Whereas if I have it like this, now here it'll shield this entire electric field. Does that make sense? So it blocks electric fields going this way. And so that's why we get no energy one way, but all the energy the other way. Okay, awesome. Let's ask you another question. So that was like a Faraday cage. I think you guys did that in lab earlier this semester too, where you did something that showed. Did you cover something in tinfoil? Maybe not. Maybe I'm just making that up. You did something. But the thing I wanted to ask you, do magnetic fields act the same way? Do you shield from magnetic fields the same way you shield from electric fields? Yeah, I'm hoping no. And I'm not going to remember what it was that you guys did earlier this semester in lab. But so you can shield electric fields because you have charges that can move around, right? But magnetic fields don't have that. So whichever that metal grating is not affecting the magnetic field that passes through it. It's just affecting the electric field. But without the electric portion to push the next magnetic field, you don't have that propagation anymore. Okay. Okay, does that make sense? Excellent. Excellent. Okay, that's how antennas work. They're kind of nice. Let me do one or two more things, and then we can look at the homework. Because so the next thing I want to look at, I want to share, is I want to look at a pointing vector. I'm just going to kind of write it down so we can see it. Okay, there's this thing, pointing vectors. It points along the electromagnetic wave. S 1 over mu naught E cross B. Where you notice we had, I kind of wrote down the thing last Tuesday when I said, well, if you cross your electric field with your magnetic field, that's the direction of the wave. So this is, but that was more of a just like a proportion, a relationship, but this is actually a solid equation here where you can put values in. So what this is this is the energy carried in an EM wave. And a good way to look at that is just to go through the unit analysis. We're an electric field, newtons per coulomb. Those are the units there. A magnetic field, Teslas, and mu naught has units of Teslas, meters per amps. Okay, and looking at this, clearly we're canceling out Teslas. That's a nice one. So we have newtons, amps over coulomb meters. Now an amp is a coulomb per second. I feel I've lost a meter somewhere, but I'll find it. Coulomb meters. This is a coulomb per second. And so notice, there go my coulombs. Excellent. Then I have I'm going to break up this. Man, I feel I lost a meter, but I'll find it. Oh, that's cheap. That's okay. I have a kilogram meter per second squared with an extra meter and an extra second. I've lost my way. I'm sorry. Give me a second. There we go. I did lose my way. Let me instead put it like this. I have Newton over meter times second. I can say meters over meters just by multiplying by 1. And so now I have a Newton meter on top. this looks much better. Newton meter on top, and I have a meter squared times seconds on the bottom. Okay, much nicer. Newtons times meters, that's kilograms meters squared per second squared. That's a joule. Okay, I have a joule. And then on the bottom, I have meter squared times seconds. Okay, so clearly we have energy in here, but there's a little more to it than that. So first, let's look at that. So what we have really is we have an energy per unit time per unit meter squared. And what is a meter squared? It's an area. Okay. So we have energy per unit time per unit area. Excellent. You can think about energy per unit time as a watt. So remember we have power, which is in watts. And so that's energy per unit time. Or you can think of this whole thing as an intensity. And so let's talk really quick about intensities. I don't think we had any intensity in 220. Okay. So we have a light bulb. It's giving off light, right? The energy of this light that it's giving off is equal to the energy of the electricity that's going into it, right? So this is a very I squared over R sort of thing, where you put current in, electrical energy as current going in, you get energy as light coming out. Make sense? And the amount of light coming out per unit second is constant. And so you can think about this light as shells coming out. So I have like this shell of light coming out, and I have another shell of light that came before this, where every second it might emit a new shell. Make sense? Now, as these shells expand, they don't gain energy. It's the same amount of energy, just spread out over a greater area. Is that all right? Which is why, as you get further away from the light source, it looks dimmer, because you're only absorbing a fraction of that energy that you might when you're closer. So for example, if you absorb this much energy, that's a significant fraction of this wave. But if you take a step back and you have, like your eye has the same surface area, but now you're only absorbing a much smaller fraction of that wave. Makes sense? And so the further away you go, so the greater your distance are from the source and your receiver are, your intensity, how bright something is going to look, is going to go as 1 over R squared, because the surface area of these shells is coming out as spheres, right? So you have the spherical shell whose area goes as R squared, because all areas do. Sound okay? And so that's what this pointing vector represents. This pointing vector right here, it represents the intensity of the wave that you're going to absorb in regards to the magnitude of the electric field and the magnitude of the magnetic field. Okay. Okay. Where the next thing we're going to look at, so look in this. So I just said the pointing vector, that's an intensity and it's proportional to the magnitude of the electric field and the magnitude of the magnetic field. but I told you just, actually a while ago, that the electric field and in fact the magnetic field as well vary with respect to time. And so the next thing we're going to do is we're going to take an average of this, because that's a much more useful number. Yeah. Okay. Okay. So like anything we do with the time varying thing, let's move towards an average. So 1 over mu naught E cross B. Let's first try to evaluate this cross product. So E, that's E max cosine kx minus omega t. B max cosine kx minus omega t. And then we have the sine of the angle between them. What's the angle between my electric and my magnetic field? I like 90, right? Because they were perpendicular to each other. Sine of 90? 1. Excellent. Okay. Looks good. And then looking at this, I have 1 over mu naught, the amplitude of the electric field, the amplitude of the magnetic field, and these cosines are identical. So you just combine them into a cosine squared. Okay. Looks good. But now I said I wanted to take an average. And so let's time average this. Mu naught, that's a constant. How about E max and B max? Constants. What about a cosine squared? What's the average of a cosine?
Zero?
Yeah, average of a just cosine is 0 because it goes from negative to positive 1. Cosine squared,
That's one. So
I think I heard it, 0.5 or 1/2. Because a cosine squared goes between 0 and 1, right? Twice as fast as cosine does. But 0 and 1. And it's symmetric, so the average is right in the middle. So you really just get a 1/2 there. Okay, so that's and I should drop that vector sign because it's not a vector anymore. So that's the average intensity. Of a wave. Okay, this looks good. Intensity. All right. I'm gonna go through that. That's good. That's good. Oh yeah, I feel good here. Okay, I'm good. Let's do some homework. Sorry, there's like lots of little things in this chapter, and some of them are definitely worth doing, and some of them are not so great doing. Okay, I want to do a few of these. We have a few right-hand rule problems. So let me look to those. Like number 2. We have an electromagnetic wave where the electric field is oscillating along the z-axis. So let's give ourselves x, y, z. So my electric field is oscillating along the z-axis. My magnetic field is oscillating along the x-axis, like that. There are two possible directions. Well, there's one possible dimension and two possible directions for this electromagnetic wave to be going. What directions can my EM wave be moving in? I like y, because when you do this cross product, you'll either get E cross B in the positive y or E cross B in the negative y. And I didn't give you enough information to know whether you'd be in the positive or negative y. But your direction of propagation is always going to be perpendicular to your two wave oscillations. And in fact, this should tell you that EM waves are transverse waves, where the direction of oscillation is transverse to the direction of propagation. Sound okay? All right. And let's okay, this looks pretty good. Okay. Number 6. And by the way, I'm going to do like one or two more of these, but if there's any that you guys want done, just let me know. So like number 6, we're looking at X-rays, part of the electromagnetic spectrum. X-rays have a frequency of 2.2 times 10 to the 18th hertz. We want to I might want to do a few more things. We want to find how long it's going to take in seconds for this thing to go 0.75 meters. 0.75 millimeters. My bad. Let me ask. Are we going to use this number? If I want to know how long it takes a light wave to go 3/4 of a millimeter, do I need to know the frequency of that light wave? No, because what speed do all light waves travel at? Speed of light, which by the way, we used to call c. I forgot to say that earlier. Okay, so tricky part here, we don't care about that. All light waves travel the same way. Distance equals rate times time. So time equals distance over rate. Do you expect a big time or a little time here? How long does it take light to move a millimeter? Fast. Good. I like that answer. That is a good answer. 2.5 times 10 to the negative 12 seconds. So that's a pretty reasonable answer there. Okay, and then the last one that I really care about, so that this is a good one for me to finish up on. We're given an electromagnetic wave, the equation thereof. It's got an amplitude of 5 volts per meter, and we don't know its wave number, but they are telling. I'm gonna write it over here. Well, I'm not gonna write it over there. I'm gonna put it right here. Minus 6 times 10 to the 9th times t plus 0.04, and we're putting this in the j hat direction. Okay, so we're given this equation for the electric field. Can you tell me the amplitude of that electric field? Of this wave? Can you tell me the amplitude of this cosine function? Excellent. Yes, where the amplitude is just the maximum value, right? So this thing, which matches up with E max, that's the amplitude. Okay, so we have 5 volts per meter. Okay, next thing we want the frequency. And by that, I mean the frequency F, not the angular frequency in hertz. What number here are we going to use to find the frequency? And you really only have 2 left. Are we going to use the 6 times 10 to the 9th, or are we going to use the 0.4? 6 times 10 to the 9th, right? Because that is what the angular frequency is, right? And that's in radians per second. So if the angular frequency, 2 pi f, is equal to 6 times 10 to the 9th, that means the frequency f is equal to 6 times 10 to the 9th divided by 2 pi, which is about 6. So I'd expect something a little less than 10 to the 9th. And not shockingly, I get 9.5 times 10 to the, this should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Good, good. Times 10 to the 8th. What unit should I put on that? Hertz. Yeah, 1/seconds or hertz. Okay, next thing we're going to be asked for is the wavelength. How are we going to find the wavelength? Excellent. You're going to use that the speed of a wave equals frequency times wavelength. So if I have the frequency and I want the wavelength, this part C, you'll just take the speed of light divided by the frequency. Which, by the way, is the equation that we're using in lab this week. What do we got? 9.5 times 10 to the 8th, 1/seconds. And this should give you 3.14 times 10 to the here, let me just, it's silly to do it that way, 0.3 meters, third of a meter. I like that. That's pretty good. Okay. Now here's the next part is a little bit tricky because I really didn't tell you the answer. But what's the direction of propagation? So the direction the wave is going, the direction of the velocity. Looking at this equation, and let me tell you, the direction it's oscillating is the j hat. So that's not the direction the whole wave is going. That's just the direction the electric field is moving, going up and down. But looking at that equation, are there any other directional variables that we might look at? What are the variables? So K, I like Kx. K is a constant, right? It's 2 pi over the wavelength. And we just figured out the wavelength. But X is definitely a variable. And that's the direction of propagation, because if I'm thinking about, if I'm trying to figure out the electric field with respect to where this wave is, that X is the direction it's going to be going. Does that make sense? So in this case, because X is in that Kx thing, this thing's moving in the X direction. Sound okay? Okay, perfect. And then there's this last one, and I guess I should have done that extra part, because there's kind of one more equation that we didn't talk about, and that is that the speed of light equals the magnitude of your electric field over the magnitude of your magnetic field. So the next thing they ask us to write down is they just want us to write down the equation for the magnetic field. Let me ask you, does it have the same wavelength or a different wavelength? Same, okay. How about the frequency? Same frequency or different frequency? Should be the same, right? Is it in or out of phase with my electric field? I like in phase, because we drew all those pictures, right, of this, yeah, where it hit the peaks at the same time, it hit zeros at the same time, it hit its minimums at the same time. So that's in phase. And where you're going to see that come in is this 0.4. So that's like a phase angle. That's how far you are off from starting at theta equals 0. So when we write this down, our cosine will have the same k, and it will have the same omega, and it will also have that same 0.4. Our max, the maximum B, our amplitude, is just going to be the electric field divided by C, given by this equation right here. What direction is this magnetic field going to be in? And let's move back. So my electric field's in the J. So I have, so I have an electric field J, that's the X, Y, Z. No error there. Okay, so my electric field is going up and down this way, right? And we're propagating along X. Which way does my magnetic field have to be oscillating in? The Z, excellent. Because yeah, that's the only way we get the E cross B to work out. And I think they want K. So that's the answer. Okay, does that kind of make sense? That's really like the most important thing, that you understand how to write down that cosine equation. Okay, are there any problems that? Are there any problems that y'all would like to do? Okay, I do not drop any of the expert TA stuff, but if you would like to go back and work on it, you can. You have until tomorrow night. Sound okay? Okay. Thank you for a great semester, guys. I hope not to see you next semester. Lab in half an hour for those who are doing lab. Online people, are you good? Okay. I hope that that I see all of your videos. And yeah, I'll be here at 2:45 on Tuesday.
So just to clear up, homework and quizzes. Homework is due tomorrow with the slides, and then quiz is due on 12th, and that's it.
Tomorrow, all of the expert TAs due and the final slides are due.
Okay. And then the slides are due on 12th. Oh, my fault. The slides are due tomorrow, but the presentation isn't due until Tuesday.
That is correct.
All right.
Okay, cool. Thank you guys.
So it's
So-
due at midnight.